Hello, everyone. Welcome to our session on operational excellence. Today, we're going to talk to two experts from top-tier operators, RES and EDPR, about how they turn data into direct value for their companies and customers, resulting in increased energy capture and reduced O&M costs. There will be time at the end for questions, so please go ahead and add your questions as we're talking in the questions box. We're looking forward to having an interactive Q&A with you. So I'm Alex Byrne. I'm a principal engineer at DNVGL. I have 15 years of experience in the wind industry, and I'm currently specializing in turbine loading topics, failure analysis, as well as services around life extension. And I'm moderating with my colleague, Michael Sherry, who's the Director of Wind Product and Business Development at Green Power Monitor. He's responsible for wind activities within GPM globally, and he brings deep domain expertise to the role, having prior experience in academia in the wind industry, and before that, in a role as Senior Renewable Energy Data Analyst for DNVGL. Next, I'd like to introduce Rosa Gandala, a chartered mechanical engineer with over 10 years experience in renewables. She is now the head of analysis and optimization at RES, based in the UK. Her team specializes in condition monitoring and performance analysis services for solar, storage, and wind assets all around the globe. And then finally, Aditya Krishna, who is the manager of predictive diagnostics at EDPR. Aditya has spent the last 5 years working in asset performance and predictive diagnostics, and he's currently leading a team that performs condition monitoring, predictive analytics, and lubrication monitoring for over 5 gigawatts of wind and solar. So welcome, everybody, to the session. I'm really excited to talk with you about this topic today. As we know, every wind project collects data, but what we don't know is how to leverage that data to meet our aggressive operating goals. And data analytics is a very quickly growing field with applications across many, many industries. So I'm excited to get into the conversation. Let's begin. I'm going to hand it over to Michael for the first question.
Thanks, Alex. Welcome, everybody. So everyone wants to know how to get the most out of their data and the assets for the least cost. Rosa, how do you and RES approach operational excellence, and how do you structure a strategy around it?
Yeah, hi. Thanks, Michael. So, I mean, to us, excellence is always defined by the client rather than ourselves. So, for us, that's the ultimate asset owner. And with operating assets, the owner and the operator then have to work as a team, really. The owner defines actually what the aims are for them, for their asset or portfolio even. It can be much wider than just a single asset. And then that operator has to, use their expertise and determine how that's actually delivered. So I would say, there's not really like a single strategy. It's about being skilled to adapt to what's appropriate. I think if I was to say a general term, it would probably just be diligence. I think that's kind of how RES sees it. We need to know how the plant should behave and validate it, and I suppose that's as far as a general strategy goes.
Absolutely. Did you have anything to add to that? And what do you and EDPR think about operational excellence and your strategy?
Sure. Thanks, Michael. So, at our end, we try to quantify operational excellence in terms of measurable KPIs. So at the highest level, these focus on fleet availability, generation, operational spend and expenses, and safety metrics. And, basically it trickles down to individual groups on how, they can contribute in meeting these high level company KPIs. So, once these are defined, it's a matter of having a clear path on how to achieve these KPIs and ensuring that we have a continuous monitoring program that is structured around ensuring that we are on track. And if there are any misses or, if we are not on track, we have a plan to address that. And I mean, another thing to note is, these KPIs are continuously evolving year on year, both in terms of what goals, we have every year. And even in terms of metrics, our KPIs probably 5 years ago are not the same or than what they are today. So it's a constant process, but ultimately, I think we look at it very objectively in terms of trying to have a KPI for every or on how we define excellence.
Thanks, Aditya. With the evolution of your KPIs, does that come from learning in your actual methods? What works, what doesn't work?
Yes, and I think it also just comes with experience, with the kind of assets that we are building, what our operating strategy and business models are. So all that is continuously evolving, and I think all of that just plays a part. Just the growth as well of the company also plays a part in what KPIs are. So I think there are several factors that contribute to how those KPIs evolve over time.
Great. So you both are responsible for creating value out of data, and one of the challenges there that I have come across again and again is that it's often hard to know exactly how much value you can create before the investment is made. So somebody is controlling the budget, and they need to decide if they're going to invest in data collection and management and analytics before they know what the return on that investment is going to be. So, Rosa, how do you kind of justify the investment or the budget when you don't know yet what value it's going to bring?
I think in some ways, the world's just becoming increasingly digitalized. Data collection is just a must to make the most of your asset, and proper management of that kind of avoids that rubbish in, rubbish out situation that we're all fond of. But I think that people are becoming less. Although you always have to sort of show the business case, and usually that's in kind of speed of processing, analysis, or ease of kind of picking up issues earlier, being more responsive, those kind of things. I think, people are generally quite comfortable with the thought of investing in innovative techniques where they trust that it's the people behind that innovation or that development are have a track record of delivering good analytics techniques, and I think it's important to try and differentiate between the kind of data engineering, the data science, the data analytics, because that does help to try and explain to someone, where the benefit's actually coming. So yeah, I think anywhere, where you're just trying to prove really the opportunity that something brings to a site. That might be in speed or accuracy or responsiveness. But yeah, I think it's not. I mean, maybe I think at Res, we've kind of been doing this sort of thing for so long. I think it was about 15 years ago we developed a so-called SCADA manager, and now that includes all the vibration data, data from all technologies, client platform views, all this kind of stuff. So yeah, maybe unlucky, just at where I work, but I find the same with clients as well.
Yeah. Okay. So your experience is that maybe we're kind of turning the corner a little bit on the skepticism about putting money behind data collection and data analytics, that there's enough of a track record in the industry in general, and then maybe with your team in particular, that the people making the decisions around budget can say, well, we trust that if there's value to be found, Rose's team is going to find it, because they have the expertise, they have the track record of finding it in the past, and this isn't, the Wild West anymore. We have seen what can happen, and it's no longer so cutting edge that we have to be worried we might end up putting all this money into it and not get anything out.
Yeah, that's a good summary. Thanks.
A further question, Rosa. So that may have been a differentiator for you 15 years ago, but now more asset management companies offering such services, and how does Res kind of stay at the forefront of it?
Yeah, well, I mean, it's definitely changed within Res. I think even 5 years ago, I'm not sure we had a single person with the data scientist role. And now, I don't know how many we have, statisticians, data scientists. And so I think you do constantly have to evolve. I think in some ways, ironically, the fact that although a lot of people are doing it, the fact that we have such a long experience, and also I think, Res was an owner of plant for a very long time as well. Now usually we operate on behalf of clients, but I think that helps in the mindset really, of understanding what's important and listening to the clients in that way. So yeah, we recruit great people, and kind of constantly try and invest in our systems, and we have we have in-house developed software, but it's kind of very much like led by experts. So yeah, I think we're okay. So
No, you're doing very well.
Aditya, same question to you. Are you guys also kind of past that inflection point where there's just trust, that further investment is going to result in further value? And if so, do you have any experience with trying out more cutting edge technology and needing to justify investment in something that is a little bit harder to predict whether or not anything's going to come of it?
Yeah, no, that's a good question, and I actually do echo Rosa's comments as well. I think maybe as an industry, we have. I think the conversation around data has become easier, and again, I think I'm lucky to work at a place where I think EDPR has been again at the forefront of of making use of data. Several years ago, before maybe it was mainstream in the industry as well. But I can give a few examples here on how we see this, especially in my area of predictive diagnostics. So in my experience, like when we are trying to say install new sensors, which could include vibration sensors, temperature sensors, to get more data from our assets, we do come across this question. So at the end of the day, our main goal is to develop a business case to justify the investment and report the return of investment to the management for approval. That's generally how we approach these questions. And for this example specifically, we'd use several inputs like say component failure rates, expected detection rates based on past experience, component replacement and repair costs, downtime costs, and of course the investment cost to prepare, these calculations. And I think ultimately conveying the proposal in an objective manner, goes a long way in moving this process along and getting the right approvals in the right frame of time. So, and of course, this process can have uncertainty when you're evaluating a new technology where, there are more unknowns. You don't know, what you can detect. But I think I'd still recommend, going through the process of actually asking these questions and, trying to go down this path. And I think it just makes the conversation easier down the line when we are trying to get justification and approvals for such projects.
Mm-hmm. Yeah, it's worthwhile to go through the exercise of setting your expectations so that you can then revisit that once you're finished with the development and be able to compare and say we met our goals in this case or we didn't, and here's why, and learn from that.
Aditya, would you be able to share a success story from EDPR's predictive analytics program?
Sure, Michael. I will be happy to walk you through some of our examples and maybe focus in on one of them. So, as a preface, I will say, 2021 is going to be predictive analytics and machine learning is going to be a key focus area for us in 2021. We have done some work, last year, and there are some projects that are further along than others. So one of the models that we have developed in house, which is probably the furthest along, is a main bearing remaining useful life model. So this is an AI-based model using physical tags that are present on the turbines, and that basically can impact main bearing performance. It was a classification-based machine learning model where we use the fall date as on the training data that was labeled as the health being scored as 0, and then the preceding months were labeled as 1, 2, 3, 4, 5, 5 being okay. So and that's kind of how the model works. The outputs of the model basically tell us what's the health score for a certain asset. So tags such as active power, wind speed, main bearing temps, nacelle temps, and a few derivatives of these tags, have been used, for this model. So overall, we've trained this model on 2 of our large platforms, with a high degree of accuracy based on initial testing. Where we are right now, we are in the process of rolling this out on the field to really get it field tested. So that's where I think the real test comes for these models. And of course, once we start getting feedback from the field, we'll be further adjusting and tuning these models. So I'm really interested to see how this plays out, and what more work we need to do at this point on this specific model.
That's really interesting that you chose a classification-based method that requires training, and so your engineers went through the data to actually classify such data as good or bad with that health score. And then was that backed up by, say, bore scope measurements of the bearing or inspections on site?
Right. So, Michael, that's kind of where we are right now, where a lot of the testing has been done on past data, on historical data, so far, and we are now in the process of actually issuing some notifications and actually backing that model up, or rather testing that model with actual borescopes. So yes, that is the next step. That's the field validation step. So I would say in the next few weeks and months, we'd be able to see if how effective is it, when it comes to actual detections. Since we are now we are using live data to feeding into the model.
How did you decide to start with main bearings?
So yeah, that's a good question. So I think there's several factors. So one of the key factors was, we do have a high degree of detection accuracy on other train components using traditional detection techniques like vibration monitoring, or even some level of temperature monitoring. Main bearings, given that it's a low speed rotation component, vibration monitoring is not traditionally very effective in detecting issues. So there was a gap there. The other factors that influenced choosing main bearing was, we had really good data. We have a large data set of failures, labeled data set, clean data set. We had good SCADA data to back it up. So that was a huge factor on why we chose what we chose. And in general, the main bearing itself, when you look at the entire drivetrain, it is a fairly streamlined component. You don't have a lot of subcomponents within the main bearing, unlike a gearbox or a generator where you have several other subcomponents. So the failure mode itself was very specific. It was a narrow failure mode as well. So all those factors, I think, just combined, and it just seemed like a good place to start. A good first place to start, where you have kind of checked a few boxes there.
Yeah, that totally makes sense, and it seems a common starting point. probably for similar reasons to what you've listed. Do you expect that the approach you've taken, this classification with the health score, would be a approach that would work with other components as well? Do you plan to try that out with other components?
Absolutely. Right now, and one of our other projects that we are trying to look at is a similar approach for some of our generator predictions as well for electrical failures. That's another, I think, area where we can, probably use a similar approach. And it can absolutely be used for, I think, several other components as well, even the gearbox and so on and so forth. So I think that approach can be, it can be used for other applications too. So.
How much data is required to train these models? You had numerous kind of failure examples in the main bearing component, and you're wanting to apply it to other components. Do you need to reach a threshold of trainable data that then the model becomes accurate enough for deployment?
Yeah, at the end of the day, I think everybody is going to say, the more the better. I would probably say at least, 20, 25 failure instances, I think is a minimum, or anything under 10, I think it's probably too early to try to deploy, a machine learning style model to predict those. But at least when you get to 20, 25 failures is when you can really start thinking about, machine learning. And also, I think you have to take into account, the failure modes as well. So it has to be a unique failure mode, or a specific failure mode with that kind of those numbers. And of course, you need to have the SCADA data to back up all those failure points as well. I think that that's a decent number to start thinking about a machine learning style model.
So it sounds like with this model, at least, it's primarily a data-based model. You didn't go into details on more of your derived channels, but it sounds like it wouldn't necessarily be classified as a physics-based or physics-informed model. Maybe, yeah, if you could speak to that, whether or not I got that right, and how you think about using physics to inform your models.
No, I think you're right, Alex. Right now, it is pure, as you mentioned, AI based or statistical model. I think in the future we absolutely want to combine, both physics based and statistical models. It's very important that we are able to communicate if a model is saying that, hey, there's a bad main bearing on Y, and what are the key drivers for that. So and that is very important for field acceptance. So we absolutely want to make sure that say a high transformer temperature is not driving a main bearing inspection. I mean, we have to make physical sense of of the various SCADA tags that we have available. So yes, in the future, I think that is an improvement area as well, where we do want to combine physics-based model. Especially we are looking at something a similar approach, say for our generator model. Where we are trying to go back and look at the physics as well. But for now, this model specifically is statistical in nature, but it does use tags that you'd expect to have an impact on main bearing performance.
Rosa, we're also interested in some examples from your side. Is there a particular success story that you could share with us about how you use operating data to identify and correct underperformance to improve your project's performance?
Yeah, gosh, we have so many with performance. With such a large fleet, we see these opportunities to kind of improve it quite frequently. I suppose the starting point for us is always to know the normal behavior. So some of the very typical, I suppose, curtailments or suboptimal losses, performance degradations. They come from often just like a technician error. leaving curtailments on after maintenance, or a software update that applies incorrect curtailments or something. That's yeah, we see that all the time. And in one case, I think the difficult one is when there is supposed to be some curtailment. So, for example, if you have a noise planning condition, and the a turbine is curtailed normally, but because of some error, um, an incorrect curtailment is applied, then that can be one of the trickiest things to find. And I think that's where, going back to kind of this diligence word that I used earlier, you can get, if you don't validate, um, that a change has been made correctly, so software update or something like that, you get months down the line, and you're either getting a local complaint, so you have to shut down the turbines, or you're identifying that there's some higher loss production, and you kind of have to work out backwards from there about where you get it. So that can be some of the more tricky ones. Yaw misalignments as well. They're hard to pick up with 10-minute data. So you kind of often find there's just a performance problem, and you're sort of doing a bit of detective work. But yeah, and I think, sometimes it's, I mean, we all know that, just because you have a high availability, you're not actually necessarily maximizing the production. Wind farms do a lot of running losses. So just understanding that normal behavior is absolutely key. And I think that's where actually there's a big benefit in having engineers look at data rather than just relying on there's a lot of data analytics companies out there that I think machine learning, especially in condition monitoring, is incredibly useful. I mean, in all applications really, but you kind of either end up with a lot of flags, because you've got a really sensitive tool, or you kind of miss things. What we don't get in wind very often is this true big data thing that would be ideal for machine learning. So I think that's where the benefit comes from having engineers look at it and say, is this what we expect from this turbine in these conditions on this site? Does this actually make sense? Is this a real problem, or is this good behavior or not?
Yeah, that's a good point, that we lack the big data in the traditional sense, and so maybe to some degree we're always going to have humans in the loop to compensate for that. So it sounds like you identify bad data through flagging it. I'm remembering what you said earlier about garbage in, garbage out. And that's certainly the case in a lot of situations for performance data, especially. I'm thinking about sector-wise curtailment and having maybe poor wind direction data to even validate. So, how much cleaning and maybe correction of data do you do? Do you think that's 20% of your job is to get that data into better shape, or are you finding that you're able to come up with approaches and algorithms that are tolerant of errors in the data?
Yeah, I think that's a hard question to answer. I'm not sure if
Mm-hmm.
I have a number on it, but I suppose I think there's a certain amount of cleaning and kind of dealing with the data. I think we're lucky in wind that we don't have the same issues like in solar. Data quality is much more challenging there.
And how much of your tools are custom built in house versus external tools, or are there external tools that you use or software that you use?
Yeah, yeah. I mean, Res does do a lot of in-house software development. We use, I suppose, things like weather forecasting, lots of different software tools for, like, for example, our control center, or also visualization of data. We've been using Tableau for a little while. So I think where you can use software that's been built specifically for that task, I think everything's becoming a lot easier as well with APIs, using the cloud. I think kind of integrating external software into your process is becoming easier. So yeah, that is really good. But yeah, we've still kind of, I mean, the benefit of building things in house is you kind of really, you can really do what you want and make exactly what you want for that specific task as well. So yeah, I think we like doing both, keeping our minds open, but also building in-house is quite important.
For both Aditya and Rosa, what technologies or techniques do you have your eye on in the next few years? Are there any promising technologies on the horizon that you think we should all be aware of?
So from our perspective, the use of cloud computing, allowing owners and operators to process, more data faster, efficiently, etc. That is exciting as far as the platform level stuff goes. As far as the specific technologies for various components from a predictive analytics go, I mean, I think looking forward to a blade condition monitoring that is holistic enough would be a game changer. A tool or a technique to really detect electrical failures and generators, converters would also be very, very useful for the industry. Failures in low-speed rotational components like blade bearings. These are pretty difficult to identify issues right now with current technologies. So, these are all interesting areas, for the industry.
How about you, Rosa? Are there any technologies you're keeping your eye on?
Yeah, I think actually I did a really good job there saying where we need to improve. I think generally, IoT gives a huge opportunity for learning more about individual components specifically. Also, kind of on the larger scale, just wind farms are becoming much more dynamically controlled with wake steering and things like that. So knowing how, I talked a lot about normal behavior, if that normal behavior changes constantly, we really have to be on top of that. So that's an interesting area for us, and also kind of hybrid sites as well, where you've got multiple technologies and the impact on that for the grid. So yeah, they're the ones I look at
Great.
a lot.
And with that, we've reached the end of our session. I really want to thank everybody for joining us. It was a great conversation, interesting insights. And now we'll go into our Q&A, so please stick around for that.
Hello, everybody. Thank you for joining us for this session. I'll pass it over to Alex to lead into the Q&A session.
Yeah, thank you, Michael. So we are going to go ahead and run through our Q&A now. It looks like we have a lot of good questions showing up, and it is helpful to the audience if you will upvote them. It helps us sort out what you'd most like to hear about. So do we have Rosa and Aditya joining us as well? Okay, looks like we're a little delayed in getting them in. So Michael, it looks like it's the two of us for the time being. So let's see if there are any questions that we can answer while we're waiting for Rosa and Aditya. Oh, we have Rosa. Okay. Thanks for joining us again. We're going to go ahead and start with a question to you. This is on common sources of underperformance, in particular silent sources of underperformance. So things that you might not necessarily notice unless you were looking for it. What are you seeing in your data at your projects?
Yeah, I mean, one common one people will know of is Yaw misalignment, that's something that's pretty hard to detect because it's, we talk a lot about normal behavior. If you see that from the beginning of the site's life, that, effectively it becomes normal behavior. So, that's probably where, Rez is lucky that a lot of sites we construct as well, so we can kind of come from that angle as well. But yeah, I think you just have to be quite diligent with looking at performance and finding those kind of things. Yeah, I'd say that's probably the most kind of impactful silent one. But yeah, I talked a lot about kind of erroneous curtailments or just instrumentation. Sometimes there are things that can cause a lot of downtime that you don't necessarily realize just because a few parameters are wrong on the turbine. So things like that are quite good to make sure you can kind of see the before and after of a software update. That's useful.
Right. Okay. So things that are present from day one, because usually we're looking for underperformance in terms of comparison of how is it doing today versus in the past, and then things that are showing up just from parameters that aren't correct, because those often don't get checked or have much visibility. Yeah. Cool. Okay, Michael, over to you.
Yeah, and that leads into a good kind of segue, I guess, like how much, or maybe I'll direct this to Aditya, how much operational time is required to identify these issues, and do you see that that is reduced when you have a fleet of assets rather than just a single asset?
Yeah, I mean, I think again it depends on what we are trying to detect. I think the time that's needed to capture any sort of underperformance or issues. I mean, on a very typical note for, I guess, identifying mechanical failures on drivetrain components, you probably need 6 months to a year, or you can probably identify it, but you probably want some trends, or some data to really have confidence. If you go, I think, to electrical component failures, your timelines are probably going to be much shorter. So, I mean, ideally, yes, we'd want as much, heads up as possible, but it also, I think, depends on the physics of the failure that you're trying to detect. And as far as the tools and techniques we use, typically we use comparison from one turbine to another. I think again, you probably want several months of data before you can really start thinking about monitoring. But of course, there are some failure modes or some things that are more obvious that you have a reference already for, say, power curves and so on and so forth, that you can probably start monitoring soon enough.
Excellent. That's really interesting.
So we have another question around what parameters do you measure? So I suspect this question is getting at what sensors on the turbines are important to look at, and then how do you? Well, the question says how do you decide when a parameter is displaying a warning? Maybe another way of thinking about that is how do you know if data is looking erroneous or if it's trending normally? And I'll address that one to Aditya.
Yeah, so for us, when it comes to predictive diagnostics, we as a standard, we are looking at pretty much all temperature tags that are coming, from the turbine, focusing on the major components for sure, and then kind of going down the list. So on a very high level, that is, I would say, our basic level of monitoring. And of course, as you go into more advanced monitoring, we are looking into vibration data and so on and so forth. But of course, other tags as well, like pressures, various turbine counters. Those are all very relevant tags when you're trying to really go beyond the drivetrain. So that maybe hopefully covers the first part of the question. As far as how do we really determine when there's an issue, I think as a base model, we use statistical techniques to identify outliers, and that's kind of been the bread and butter for us. I would say for a good amount of time, and we probably start there. We come up with some statistical tools that calculate standard deviations, and we assign thresholds based on those standard deviations. Whenever something goes out of whack. And again, that from there on, you can adjust your thresholds based on actual field data and really adjust that and really hone it down to specific failure modes or even specific sites.
Nice.
I'll put another one up there, and maybe put this to Rosa. It's a generic question. Which data gives the most value?
Yeah, I mean, so I think everything that Aditya just said is definitely true for us at Res. We, I suppose, talking just about the kind of turbine data in particular, in addition to kind of temperature or vibration for condition monitoring, for performance, the wind and kind of everything to do with the performance, the kind of wind performance of sites is really important. Then I think we also use we do a lot of compliance assessment. So yeah, things like electrical quality is also something we'd look at. Hopefully that's the question.
Great. No, I think that answers the question. We have a question here about, and I think both of you could probably speak to this. Question is, what rationale do asset owners follow in deciding to insource or outsource data analytics? I know both of you have a pretty well-established team, so maybe this question would be, if you were to advise an owner that doesn't have a well-established team, whether or not they're facing the question of insourcing or outsourcing their data analytics, what considerations should they take into account? Let's start with Aditya, and then Rosa, if you have anything to add, jump right in. Aditya, I think we may have lost your volume. Okay.
Sorry. No, maybe you can hear me now.
We can hear you now.
Sorry. So I think for us, I think it ultimately comes down to the overall company strategy. If you are an engaged operator, and that is a longer term strategy where you do want to have control over the analytics and the data, and really want to form a team around it, I think you have to just start taking the first steps into developing that team. And of course, you have to kind of go out, look at the market, what's there, what's available, and probably again it comes down to developing a business case and seeing if hiring folks internally to do the work, how does that compare to some of the external offerings. But all in all, I do think the overall strategy is important in deciding what you want to do now, what your long-term strategy is.
Great. Rosa, do you have anything you want to add?
I mean, yeah, we see kind of owner operators, and then we see the kind of large asset management fund type owners within the industry, and I think that's what Aditya's kind of saying, like different owners have different strategies and want different amounts of information. We see owners all types wanting more information, and the kind of question I suppose is, do you want to kind of invest in the people, and it is quite a big I suppose back office really to in order to support that kind of predictive analytics and do it well, and so it does need to be a kind of significant and long-term investment to almost get up to date. And the alternative is that you can kind of work with analytics provider or an asset manager who has that analytics capability, that can provide that and give you kind of exactly the information you want for your KPIs and the way you want to run your kind of strategy and your portfolio. So yeah, both, we see both, but it's as the teacher said, strategy based really.
That makes sense. Okay, we still have a bunch of questions, and I just want to encourage the audience to vote so we know which ones you want to hear most about. Go ahead, Michael. Ask the next.
Sure. There's one here which is I can address to both. Which engineering strategies do you use for the fault detection, failure modes, and lifecycle management of wind turbine components? Maybe if you'd like to go first, Rosa.
Yeah, sorry, I just reread it for myself. So we do have we do use obviously all the vibration data for fault detection, and I think as far as what kind of life extension or repowering decisions and all that kind of load estimations, you do need very good quality long data sets. We have sites that you kind of look at the data after 15, 20 years and you're like, ooh, didn't realize that a sensor wasn't working or something. We have seen that with clients in the past, and so it's important to basically keep that data healthy and make sure you're regularly checking that it's good quality.
Absolutely, that's a really important point because you can't really get the data back if it's ruined in the past. Did you have anything to add to that?
Not a whole lot. As far as detection, strategies or techniques go. I mean, primarily, as Rosa mentioned, again, we also use a ton of vibration data. We use temperature data to again identify outliers, and also, we have a lubrication monitoring program as well. So those are probably three key pillars as far as what techniques we use for predictive fault detection as of now. And of course, I mean, for the other stuff in terms of life cycle management for components, we have a full as every OEM or operator would have a full maintenance strategy around on how to maintain your equipment through periodic maintenance activities and of course reactive maintenance as well where needed. So.
Great. Okay. I think this question is best addressed to Aditya. So the question is about exploiting the presence of multiple assets of the same type. So how well do your machine learning models transfer across different turbines, maybe of the exact same type at different sites, or maybe similar types, but not the exact same?
That's a good question. I mean, as I said, we are still, I would say, early on in our experience. But even, with this one model, that's a little bit further along, we did see differences. Even though the model was, gave pretty high accuracy on, say, 4 out of 5 sites. We had that one site where, the model did not really fit very well. So we did come across that. And so those are things I think you have to kind of take into account and, make sure, your model is applicable to, different, platforms or sites that, you're evaluating. A few things that we thought, could contribute is, again, the local conditions that exist on a site. Maybe you have a site with high turbulence or, some specific loading conditions that is really impacting, the life of a certain component. And that may skew your model one way or the other. So those are, I think that's where you go to that next level of analysis. And honestly, I mean, at that point, maybe you need to just come up with a specific model for that platform or for that site, and just look at it a little bit more differently.
Interesting. Okay, Michael, maybe we probably only have time for one more question. Do you want to do the last question?
Sure. Which one? There's a couple of upvoted questions here. I guess that's kind of been answered. So maybe we'll go the AI question. How do you think AI and machine learning could help on assessment of wind turbine components? You kind of addressed that in your talks, but have you deployed AI algorithms other than the main bearing kind of model that you talked about, Aditya, on your assets under management? Maybe I'll address that to you, Aditya.
Sure. Yeah, I mean, as I mentioned, that the main bearing one is probably furthest along, but we have plans of expanding this to a few other components, and trying to see if we can use AI for generator electrical failure detections, and of course, just basically plugging the gaps that traditional vibration monitoring or temperature monitoring cannot get us. That's kind of what our strategy is, to use AI to see what gaps can we really fill on our monitoring program that traditionally vibration monitoring cannot. So essentially, we'll probably be just taking one problem at a time. I gave an example of main bearing, generator, maybe blade bearings in the future, and other components, hydraulic systems, so on and so forth on the turbine that may come in the future.
Fantastic.
Awesome.
Rosa, do you have anything to add?
Yeah,
I think there's time.
Yeah, we've so our condition monitor team, we've kind of been looking at gearboxes for a very, very long time, and started to kind of use more AI. And yeah, I mean the results are really impressive, and we're in a position where we can kind of compare different models as well, and test them, which really helps to increase your confidence quickly. So yeah, using particularly with temperature, which is a very, very complex in turbines, because you've got the air conditioning systems, you've got the weather, and so many different aspects to it. And I think that's where AI is really helpful, because it can take in so many different dimensions, where it's kind of traditionally quite hard to build a kind of a manual model like that. So yeah,
Absolutely.
we've definitely used it in good applications.
And as you mentioned, it's one of a suite of tools that you can deploy in the process of efficient O&M.
Yeah.
Awesome.
Alex.
Okay. Yeah. Thank you, Rosa and Aditya, for joining us. It was really great to have this conversation. To our participants, I'm so sorry that we couldn't get through all your questions. You have really good questions, but if you stick around, we will be joined by DNVGL, Meet the Experts, just in a moment, and we'll have a chance to do more Q&A with them on this topic.
Hello, welcome. We have Malcolm Heath joining us. Kim Mortstock is also joining us, and hopefully Alex will be back. And Pau Pujdalez, I hope I got that right, Pau. I've been practicing. So yeah, you just heard some really interesting questions to Rosa and Aditya, and we'll just continue on the same kind of line by answering questions that have been upvoted by participants in the audience. So if you'd like to see a question, please upvote it. And I'll just throw questions to each of you as they kind of come in. So I think if Alex is back online, did you want to give a brief introduction of our experts at the moment?
Yeah, thank you. Thank you, Michael. We'll just do brief introductions of each person. So we'll go around the horn. Kim, would you like to start?
Sure. Hi, I'm a principal engineer with the DNVGL, and I've been working there for about 14 years. I'm currently mainly working with performance of operational assets, so anything to do with the production, as well as the cost, reliability, and I get involved quite a bit in benchmarking.
Great. Good to have you, Kim. Malcolm?
Hi, thanks, Alex. Hi, everybody. So I'm Malcolm. I'm the Business Development Manager for WinGemini. So that's our online digital twin product. I guess we'll talk about it quite a bit, but it's a product for performance monitoring and so on. I've been with DNVGL for 11, nearly 12 years now. So a lot of that time I've been on, similar to Kim, operational analysis of operating plant. I was also involved with our wind farmer software for a while, so you might recognize me from there. Mostly operational analytics is my thing now.
Awesome. Great to have you, Malcolm. And Pau.
Hello, everyone. This is Pau from Green Power Monitor. I'm currently the global head of product at Green Power Monitor. So basically coordinating and making sure that all our products for asset management of wind technologies, but also solar, battery storage, so hybrid sites, as was mentioned previously, are effectively developed and fulfilling our customer needs.
Great. Awesome. Well, it's really great to have you guys. We're going to continue the Q&A from our prior panel. So I'll go ahead and throw out the first question, which is actually a repeat. I'm interested, Kim, to hear from you on the question of silent underperformers. So what do you see when you're looking through data in terms of causes of underperformance that maybe wouldn't be clear if you weren't looking for it?
Sure. Well, I thought that our previous speakers, I nodded along to everything they said. So just to try to continue from their points, Rosa mentioned some technician errors. So one of the things we do see occasionally, but on many occasions actually, are some sort of control errors. So rather than error, like someone typed in the wrong control parameters, and for whatever reason, it doesn't get caught. So in one case, it was turbines that were derated for a year and a half. So that's not too common right now, but it still happens on wind farms where people aren't regularly looking at the data. There's one I'm looking at this week where the power curve changed shape, and it was underperforming about 10%, more or less, for 3 or 4 years. And so the turbines were operating, they had good availability, but they weren't operating quite the way they should have. So I think Rosa's point again about what is the normal behavior and just knowing whether or not you're achieving that. And then along those lines as well, certain parameters. So are the bat curtailment parameters set correctly, or the wind sector management parameters? If it's a certain direction sector, is the yaw position correct so that you're getting the right direction sector? So there's kind of issues around the margin that we see.
Yeah, super interesting. I think there's a lot of ways in which we might be producing less energy than we think we are, but not even realizing it. If you don't mind, if I could keep it on the hook for another question. You mentioned, comparing to normal or expected production. How do you come up with your concept of what is expected?
Yeah, that can be a real challenge. So there's different aspects to it. One is ideally you have a power performance test. And so you have a measurement on the site of how those turbines are performing. And that way you at least know if, given the wind resource, the turbine is producing the amount of energy that you expect. And we've had a lot of trouble on sites where those are not there, because then you don't have an independent measure of the wind speed, the resource. And so you don't know if the performance you're seeing is what you're supposed to have or not. You can go through and look at data over time and look for any changes. That's easier than if the settings were incorrect in the first place.
Great. Okay, over to you, Michael.
Yeah, following on from that point, there's a question here from the audience about how important the measured wind speed, measured free stream data is to digital twin models, and maybe I can open that up to Malcolm to kind of comment on that and how beneficial digital twin models can be.
Yeah, so so measuring the wind speed is or should be a really valuable and really useful thing. So your fundamental judgment of how well a turbine is performing is the power curve. That's really that's what you buy from the manufacturer, and that's based on the wind speed. But in reality, it's very, very difficult to know what the wind speed actually is that the turbine's experiencing. So what's arriving upwind of the rotor. Partly because nacelle anemometers are downwind of that rotor, and the wind's been messed up by the rotor by the time it gets there. But also because they tend not to be terribly well maintained. So when we look at through the lifetime of a turbine, you can see shifts in the data that's been recorded by the anemometer because the anemometer's maybe been broken and replaced with another one that's differently calibrated or something, or some settings somewhere have been changed and the calibration settings that are applied to it have been changed, and so the response changes. So things like this. So reliable measurements of the wind speed tend not to come from the turbine. And so there's a couple of things we can do about that. One is to attempt to infer what the wind speed was from the way the turbine's behaving. So that can be counterintuitive when you're looking for performance issues, but it can be useful when you're looking for other aspects, perhaps in terms of assessing fatigue or something like that in a turbine. But also more commonly is to just look at the other parameters of a turbine and just base your judgments on that. So more physical measurements, or more direct measurements, say for example the pitch settings, the rotor speed, this kind of thing. Those are much easier to measure and much more reliable. And so we tend to use those as our judgments of normal behavior of the turbine. As Rose was talking about, assessing underperformance as being something different from what you normally get. So we tend to judge normality and normal behavior on the pitch performance and the rotor speed performance and the power, those three parameters, and they're much more reliable. But when we're talking about kind of hidden underperformance, another cause of that is when parameters like that are incorrectly measured. So problems do happen with those sensors as well, and again that can throw everybody in terms of their analysis of performance. So that's another way of hiding things. So so perfect measurement of incoming wind speed would be great, but it's never there. Yeah.
Yeah, so you use multiple sensors to identify underperformance, not just the nacelle wind speed. You can build up models, I guess, and maybe I can throw that open to Pal. In terms of kind of asset management software, how are products tracking and alerting customers to these particular issues?
Yep. So it's essential for any asset management software or software for operating assets such as ours to have a strong alerting or alarming system to avoid what Kim was mentioning, right? Going 3-4 years without even noticing you're having problems in your assets. So effectively, it's very important to have a robust alarming system that not only alerts you when things happen, but that you can very flexibly build in or relate your models to alerts so that you will get notified at the moment when something happens. That is one thing that's essential, that you can tailor your alerts based on your needs, based on the individual moments of a power plant. This is seasonality of power plant. You can adapt the alerting system to different conditions, but also that you can also relate your alerting system to a way of tackling those alerts, right? And that's when we get into ticketing systems, O&M systems, where you can effectively act or generate tickets, assign them to your set of operators, to your companies that you have subcontracted for O&M, depending on the way you operate. But you can flexibly also build your ticketing tool around your alerting system. And is something that our systems allow to do, and that has been found to be really useful in just acting on issues when they happen and not letting them go on over time.
Great. Okay. Pivoting a little bit, Malcolm, I think this is going to be directed at you. We've got a number of people who are really interested in blades. So what have you seen in terms of sensors or models addressing blade reliability? Is there anything that we can do right now to see or foresee blades that are that are damaged or in the process of failing?
Yeah, so yeah, I'm not really a blade expert, I'll be honest with you, but one tool certainly we have in WinGemini for looking at blades, particularly is aiming to detect an imbalance in the blades, so that the blades can become imbalanced. Perhaps there's literally the physical mass throwing them out of balance. More commonly, it's maybe a pitch issue, so one of the blades isn't correctly aligned with the other two. In terms of pitch, but it can also happen from blade damage as well. So you can get blades, maybe the cracked blade flaps around a little bit, or its aerodynamics are spoiled, or something like that. But basically, we can look for the effects of that kind of imbalance because of the way that it affects the whole powertrain and physically affects the nacelle. So you can imagine as a rotor rotates, if it's not properly balanced, it introduces oscillations in the nacelle, and it also speeds up and slows down the rotor as they go around and things like that. And the effect of that ripples through into rotor speed measurements, and even the actual power output can change as the rotors move. That's something you don't see for normal 10-minute SCADA data. It's all averaged out there. But when you look at the higher frequency stuff, if you're measuring at perhaps once a second, something like that, then you can see it in the data there. And that gives us, we can use that as a tool to identify imbalances in there. So that's a way for us. That's the best way, I guess, we found out of finding blade issues just from data without physical inspection.
Great.
Yeah.
Over to you, Michael.
Sure. That brings up kind of a question whether you have vibration data, and maybe I'll throw this to Kim. As vibration data is quite complex. So, what kind of performance monitoring would you recommend for kind of an average size wind farm?
Well, I mean, vibration would be one component of that, right? So it's becoming more and more standard, if not almost entirely standard, that the new turbines are installed with condition monitoring systems, vibration sensors. That used to be a retrofit, so there was a cost-benefit question there. But now I think we're past that question. So basically having somebody monitor the vibration signals, and whether that's the OEM, if they're still maintaining the turbines or monitoring the data, or having in-house expertise. It does take extra tools. It's a higher data frequency, so not just the 10-minute SCADA that we often get. So, I mean, essentially, whatever you can get on the turbine is going to feed your data models to understand. So that's what, for vibration monitoring, the answer is yes. Wherever they can install sensors. But then what other types of performance monitoring, if I can kind of broaden that question a little bit, for your wind farm? I really liked how Aditya mentioned KPIs. So then you kind of know where you're aiming. So, you're looking at availability, you're looking at production. Ideally, you have some measure of the free stream wind speed we mentioned. So what is the fuel that's going into your wind farm? So that kind of helps you understand whether or not you're going to meet the generation goal, as well as reliability. So, how do you accomplish those things? We also mentioned there's different tools you can use, whether you have in-house tools, whether you have WinGemini, GPM, or any other of the competitors there. But essentially, you want to, as Rosa said, know the normal behavior, monitor at least the 10-minute signals, as well as the high-frequency condition monitoring data. And you're looking for whether you're meeting the KPIs, are you making the production you think you should be, and whether there are changes that we discussed. So I think all those things are important aspects. And in some ways, it's insurance. That's how I like to think about it, that many wind farms, we're not seeing these issues that we're talking about. They're going along just fine, and you might think there's not a cost benefit there, but you still would buy insurance so that if an issue does come up, you will save a lot of money by identifying it quickly.
That's good perspective, Kim. Okay, I think this question's probably best suited for Malcolm. The question is on big data. So why don't we use true big data in operating performance and maintenance failure analysis? I am going to maybe put my own spin on that question. I think the question might be, couldn't we do unsupervised learning or deep learning with wind data? Why not?
Yeah, so I think this is picking up on something that Rosa said, and I think what it boils down to is that actually historically we've not done a good job of collecting data. So certainly when I talk to a lot of customers, wind farms change hands quite often, and data often gets lost when that happens. Back in the early years, when looking at old wind farms, storage of data was an expensive thing to do, and data just got thrown away. And so as an industry, we've a bad track record, I think, of collecting data, and so we're only now kind of struggling to learn how to mine that data and really get value from it. But then we find problems that we've got a whole myriad of different turbine models, all of which behave in slightly different ways, and different versions of the same model that behaves differently, and control strategies get changed through the lifetime of a turbine, and this kind of it's enormously complicated actually to learn what this elusive normal behavior, and what is the correct behavior of a turbine. It's very difficult to learn, even when you have got a great big pool of data to work from. And I think we're still finding out that a lot of things has to be done really project by project and site by site, and you try and mine the data for that project and learn, build up your learning models that work on the data from that site. And it's very difficult to extrapolate from one site to another. And technology will get there. I don't doubt technology will get there, but at the moment it's still quite challenging to do that. And so so the industry is catching up. Definitely, the number of people involved in analytics, the amount of research that's going into it, the industry is kind of catching up on there. But it's come from quite a difficult. We're working in a difficult environment, and it's got some quite difficult challenges to overcome to really make the use of all that data that everybody talks about all the time.
Right. Just the general maturity of the market. Pao, do you have anything to add to that?
Yeah, definitely. I totally agree with Malcolm. The market is maturing, and I think we're learning how to deal with data and what tools we can extract from data, right? And I agree. So many farms they don't have access to data, or their data is underutilized, right? So what we want to do is be able to have tools that maximize or provide this operational excellence to our wind farm. The only way of doing that is having of course the right tools and the right, let's say, approach on how to deal with data. We might get into situations where we're going to be going to very high frequency data under 1 second resolution, etc. So how to deal with all of that data? We need to be ready. We need to have our systems ready for that. What can we harness out of that data is also very important, and as we were discussing in the session before, we need to have organizations ready for that, right? Be it through internalizing our teams of data scientists, or getting the right teams, or externalizing the right teams, or purchasing or using the right tools to achieve that. It's absolutely necessary. We need to be very flexible in the way we use data, in the way we secure data as well. The more data we store, the more data we use. We're also being able to, or having to be custodians of that data. Otherwise, we can expose lots of information, and we may end up with potential problems. So we need to have a secure and robust system that allows not only to use data, but also store data in a very efficient and scalable way. And just to finalize that point, I think the point that was mentioned previously of going to cloud, but also going to openness, integration, or API friendliness. To integrate solutions and other tools, it's essential. In the end, we're running towards achieving a global data lake, and through anonymization of data, but using the potential of the data that everyone has around us. So it's important to have these systems ready and available for sharing data with others.
Yeah, great. Yeah, great points. I mean, we can't do any analytics if we're not collecting and managing and storing the data appropriately. Great. Over to you, Michael.
I got booted out of the session just briefly, so if you want to answer the next or ask
why
the next question,
don't I
Alex?
keep going? Okay, I think this question is going to be either for Michael or Kim. So it's on yaw misalignment, and the question is, to correct yaw misalignment, you need to have a nacelle-based LiDAR. But is there any other way that yaw misalignment could be, identified and corrected without the use of a LiDAR? Let's see, Malcolm, go ahead.
Yeah. So we've quite recently developed a technique for doing that based on SCADA data. It's quite powerful, but not 10-minute SCADA data. That things get too averaged out there. But we look at higher frequency stuff, so anything that once every 30 seconds or faster than that. And basically, we work on the principle that in reality, turbines don't spend, even a perfect turbine doesn't spend all its time pointing directly into the wind. So to save wear and tear on the yaw motors, it lets the wind drift offline for a little bit before it then corrects. So actually, as turbines are operating, there's always data being collected when the wind is slightly off what the turbine thinks is true, is the correct yaw. And so by looking at that on a high frequency, we can see actually when the wind's coming from 3 degrees to the right, actually that's when the turbine's working most efficiently. That's when we're getting the most power. So we can say, oh well, if you adjust your turbine so it's normally aiming 3 degrees to the right of what it does, then that's going to give you your optimum performance. So we've got that technique now which we're using, and it's we can do that as offline analysis, and we're working to bring that into WinGemini quite soon as well. So that's great. That's a real chance to do a much lower cost analysis to pick up your misalignment, which is one of your classic hidden performance issue.
Totally awesome. Okay, I think we are kind of coming to the end of our session. Michael, is there any pressing questions you want to make sure we get out to our panel before we wrap up?
Well, yeah. Let's go. So I'll throw this one to Kim, and there's one here that says, what potential savings in O&M costs compared to the overall economic model of a wind farm? Are you able to comment on that?
What is the potential savings? Okay. Well, I think this is going to be very site specific. It's certainly, we've talked a lot of aspects. I think the major one for O&M savings is going to be on, as Aditya was discussing, so having some sort of reliability review. So looking at the condition monitoring data and so forth. So then you're looking at the condition of your gearboxes, your generators, your major components, your main bearings, as you mentioned, having a model for. And so being able to schedule the replacement of those, having targeted inspections when there seems to be something happening out of the ordinary, that's definitely going to be where you'll see the most O&M cost savings.
Thanks so much.
Awesome.
Over to you, Alex.
Okay. Yeah. Well, thank you, Malcolm, Kim, and Pao. It was really great to have you here answering the questions, being the experts in the room for us. So we're going to go ahead and wrap up the session. Thank you for participants for joining and asking all these great questions. Have a great day.
Okay. Thanks, everybody.
Thank you.
Thank you very much. Bye-bye.